So I'm going to have a look at another type of biofuel, and this time we're going to look at biodiesel. Now, biodiesel is basically just a mixture of different esters. We know that esters are standard organic molecules formed by condensation reactions between alkanols and between carboxylic acids, but that's not important here. What's important here is that biodiesel is just this mixture of these molecules that we can call esters. Now, in this way, biodiesel is the same as regular diesel. Regular diesel is also made up of a mixture of esters. And so biodiesel, what we do is we burn these esters to produce energy. So biodiesel is in fact created from one of two sources. Biodiesel can be created from vegetable oil or animal fat. Now, both vegetable oil and animal fat fall into the same category of organic molecule, and this category is called the triglycerides. Now, here I've drawn the standard sort of structure for a triglyceride. So what we have is we have these three carbons in the backbone here linked together like this. So these three carbons are bonded together, and they each have the two end carbons have two hydrogens, while the middle carbon has one hydrogen. Now these three carbons are then bonded to an ester linkage. They are each bonded to their own ester linkage. So we know that this part here is what we can call an ester linkage. And so each carbon in our backbone chain has its own ester linkage like that. And so when we're looking at this ester linkage, if we're looking at a regular ester molecule, then we know that we know that our ester linkage looks like this. We've got the double bond oxygen and then an oxygen, and then we have two alkyl groups on either side. Now we know that in this basic structure, if we're looking at a regular ester, then R1 stems from the alkanol that reacted to form this ester, and R2 stems from the carboxylic acid that formed this ester. Now that's if we're looking at regular esters. However, this is a triglyceride. We simply have an ester linkage. And so what we need to remember is that we have these three carbon backbones, and this three carbon backbone is on the alkanol side of the ester linkage. It's bonded to the single oxygen side of the ester linkage. And then we have an extended alkyl group on the other side of our ester linkage, represented by the letter R. Now over here we have two other very important molecules. So what happens with these triglycerides, with these vegetable oils and animal fats, is that they react most often with methanol. So if we write in here plus methanol, then the reaction that we use when we're dealing with biodiesel is we take our triglycerides, we react them with methanol. What we do is we produce a molecule called glycerol, as well as some molecules that we can call fatty acid methyl esters. So we have triglyceride and methanol reacting to produce glycerol, and triglyceride and methanol reacting to produce glycerol and fatty acid methyl esters, which are a special type of ester. And so this reaction occurs in the presence of water and with a potassium hydroxide catalyst. So we have our triglyceride reacting with methanol to produce glycerol and some fatty acid methyl esters. So what happens is we know that if we have our methanol is quite straightforward with this structure here. And so if we were to put some coefficients in this, we have three methanol molecules reacting to produce one glycerol, and as I've written down here, three fatty acid methyl esters. Now a fatty acid is basically just a carboxylic acid with a very long with a very long main carbon chain. And so we know that esters, so if we're dealing with fatty acid methyl esters, that means we're dealing with esters produced from a very long carboxylic acid and a methane molecule, or sorry, a methanol molecule. So what happens, so that means we've got our CH3 on the alkanol side of the ester linkage, like that. Then here we have our fatty acid, our very long carbon chain, represented here by the letter R. And so that is what happens. We have our triglyceride reacting with 3 methanol molecules to produce this molecule called glycerol, which can be kind of viewed as, we can view the glycerol as if we've cut our triglyceride here and added some hydrogens onto these 3 oxygens. That is one way that we can view our glycerol molecule. So it's very similar to the backbone of our triglyceride molecule. And so what we have is we produce some glycerol and we produce 3 fatty acid methyl esters, which are esters with very long carbon chains on the carboxylic acid side of the ester linkage and a methyl group on the alkanol side of the ester linkage. So fatty acid methyl esters, sometimes abbreviated to FAMEs, F-A-M-E, fatty acid methyl esters. Now, in this case, we've shown the reaction of our triglyceride with methanol to produce glycerol and fatty acid methyl esters. And in fact, it is possible for us to in fact react triglyceride with ethanol rather than methanol, still in the presence of water, however with a slightly different catalyst, maybe sodium hydroxide. So this reaction will go ahead if we replace methanol with ethanol and potassium with sodium. However, rather than producing fatty acid methyl esters, we'll therefore produce fatty acid ethyl esters. However, this reaction, if we're using ethanol rather than methanol, has some practicality issues that make it less efficient and less effective for commercial production. So in almost all cases of large-scale production, we're looking at vegetable oils or animal fats being reacted with methanol to produce glycerol and fatty acid methyl esters. What's important is that it is these fatty acid methyl esters that form our biodiesel. They are the mixture of esters that we label biodiesel. So we burn these fatty acid methyl esters to release energy. So biodiesel can be used in lots of different ways. We can use it can be used maybe some fuel. It can be mixed with diesel, with regular diesel fuel, and used as a mixture. So we might have diesel fuel containing 5% biodiesel, and that called B5, or 10%, maybe some diesel fuel containing 10% biodiesel. And eventually, with some cars are actually capable of using 100% biodiesel, but it is a slow process. However, again, like our other biofuels, these triglycerides consume carbon dioxide as they are produced. So the production of triglycerides uses up carbon dioxide, and thus when we're releasing carbon dioxide, when we're burning these esters, that carbon dioxide is simply the same carbon dioxide that was absorbed in the production of these triglycerides. So that makes the use of biodiesel, which is produced from triglycerides, a carbon neutral process, the same as ethanol and biogas. So that's pretty much all we need to know about biodiesel. So we just know that there are lots of different triglycerides with different alkyl groups on them. What we do is we hydrolyze the triglyceride with water and some methanol to produce glycerol and these fatty acid methyl esters, and they are the things that we are after in order to produce our fuel. They are the fuel that we are using and that we are burning.